So hello everyone, welcome to the academic seminar of the day. Today we have a lecture from the University of Kyoto, Kyoto University, about renewable energy for electricity, potable water and chemicals. So I'm Khawla from the J-MENA project, and we are glad to introduce most of the notch topic research fields of Japanese universities. Today we have this academic seminar, and in this occasion we would like to present the following or the upcoming events also. So keep an eye on the SNS platforms of the project where you can register and follow all the news of the project as well. So, and we are glad to see you again next Tuesday with the Begin Fair. So do not miss the opportunity to meet the representatives from Kyoto University of Advanced Science, Kobe Institute of Computing, and Osaka University. So if you'd like to learn more about the educational system, how to apply, and the application requirements, you can learn many things from these fair. And we are glad to let you know that all the recorded videos from the Study in Japan fair are uploaded on the YouTube channel. So just click on our YouTube channel and you can watch all the recorded videos as well as the interviews done with the successful MEX scholarship students. So you can watch and know more about the application process and how to get a successful application. We thank you for joining us through the J-MENA platforms. You can learn more about student life, facilities, and life in Japan through our SNS platforms. And you can contact, of course, us through email, Instagram, Facebook, and Twitter as well. So we thank you again for joining us, and we welcome Ogawa-sensei to start the lecture. Sensei, the stage is yours. Thank you. Ogawa-sensei, we can start now. So maybe. So we invite Ogawa-sensei to start the lecture. Could you, okay.
Sorry, can you hear me? But I cannot hear at all now. Sorry, just something problems.
Okay, we can hear you perfectly.
Sorry. Please wait for just 1 or 2 minutes. Sorry.
No problem. Yeah, in the meantime, so we can ask you to register before the academic seminar. So you make sure to receive the Zoom link and join us before time. So we wait for Ogawa-sensei. So those who are having questions about the lecture, we ask you kindly to write your question or inquiries in the chat box. And then after the presentation time, we will have Q&A session where we can discuss and answer all the questions with Ogawa-sensei. Thank you very much for your cooperation, and we're looking forward to seeing you soon in Japanese universities. So we wait for Ogawa-sensei to make sure everything is okay. So Ogawa-sensei, can you join us now? Sorry, we cannot hear you, Sensei. Yeah, the voice is not clear. It's okay, Sensei, take your time. よろしくお願いします。
Can you hear me?
Yes, perfect now. You can hear.
Okay, sorry so much. Okay, now it's great. Okay, so okay, let me start my presentation. Sorry about that. Yeah, so there's some trouble about my mic and earphones. Okay, let me share my screen firstly. Thank you coming today. Okay. So basically, I'd like to talk about the renewable energy for electricity, potable water, and chemicals, especially for ammonia. This is Takaya Ogawa. Nice to meet you. Here is in Japan, and the time is evening 6 p.m. and maybe it's a good evening, or for you it may be good afternoon or good morning. Anyway, so this is international online seminar, and thank you for coming today. So as an icebreaker, I'd like to ask one question. Firstly, this is the question about the energy consumption in the world. This is very huge. 30 petawatt hour. It's almost the unit is like this. This is year, so 2019. This is the year before COVID-19. So this is I think usual energy consumption. So how much of the sunlight is shedding on the earth? Please think about that. Answer one as 15, it's almost 15, and 2 second as 15 multiple 10. So it's 500. Start as 50,000 or as 5 million. How do you think this? Maybe too easy for you, maybe. I'm not sure. Anyway, the answer is this. So 5 million % is shedding on the earth. So it's very huge rather than the energy consumption in the world. So the important thing is energy, not the amount. So maybe not efficiency. Cost is the most important thing. So I will talk about this. So the table of contents for today is shown here. So I will start from self-introduction, and I will talk about the general information related to renewable energy. And this is usually utilized for generating electricity, but it can also utilized for potable water and also chemicals. And I would like to introduce recent researches, especially the progress of ammonia synthesis. And I would like to introduce my research, water, electricity, ammonia nexus production. These three, basically. So from self-introduction. Thank you, Asa. This is Takaya Ogawa. I'm now assistant professor at Kyoto University at the Graduate School of Energy Science, and now tenure track position since 2018. And also successfully I got the tenure, and I'll be an associate professor from the next year. And also my background is chemical engineering and quantum chemistry calculation and material science and electrochemistry. Basically, today's presentation is related to chemical engineering. And my research interest is life cycle cost assessment. Assessment means amount of CO2 emission, and also the techno-economics assessment. Sorry, it's equal to cost actually. And also, I also doing the research about experiments like synthesis and analysis of electrocatalyst and electrolyte and electrocatalyst and catalyst. So more details, proton conducting material and catalyst for ammonia synthesis. So let me start about the general information of the cost of electricity based on renewable energy. This is information from IRENA, so reported in 2019. It's very, almost all of the renewable energy getting decreased in terms of the cost, especially the solar photovoltaics for the cost is very decreased like this. So it's almost close to the price for the internet sector in 2019 in USA. So it's very close. And so it's almost comparable for the industrial electricity sector, so electricity in the internet sector. Anyway, so not only for the photovoltaics, concentrating CSP, concentrating solar power, offshore wind, onshore wind. So these are getting decreased. Top 10 list of the lowest solar power in the world is shown here. And this shows much more lower than the data before I showed in the previous slide. Oh, so I and based on the data, so PV is photovoltaics in 4% of the desert area is enough to generate the whole electricity in the world. So it's basically the amount of energy in the world is very huge, and actually the price is getting down. The challenge is solar energy is excess electricity invested in the daytime. So demand in the daytime is not so huge actually. So the battery which can storage the electricity is very useful, but it's very generally too expensive. And arid semi-arid region normally requires not only electricity, food and water rather than electricity maybe. So the excess electricity and waste heat can be utilized for the production of potable water and chemicals. This shows excess electricity in the daytime. So it should be utilized for more used for more beneficial things. Like so potable water and chemicals. And this is an example of the desalination of seawater. You may know about this as MSF or March effect, so MED, multiple effect distillation. And these three are very important technology, especially sea reverse osmosis, SWRO is very important because this requires the small amount of total energy. But actually, electricity is not, so other two technology doesn't require the electrical energy rather than SWRO. It means this may can utilize the waste heat rather than SWRO. So this is the advantage of these about two technologies. And if we focus on the chemicals, it can be, of course, the products, and also it can be an energy storage. If we think it can be energy storage, the criteria for the energy storage is right and very abundant elements such as hydrogen. So hydrogen gas H2 is one of the options to be stored as an energy carrier. Here is a simple reaction, water electrolysis. So water can be decomposed by electricity, and it can be hydrogen gas and oxygen gas. But however, hydrogen gas has an explosion risk, and liquefaction is very difficult. And compression consumes huge energy. So these are the disadvantage for hydrogen as energy storage. But if you look to carbon, there's many choices. Methane, methanol, formic acid, like this. So there's a versatile products and safe and easy handling. Actually, if we choose formic acid, it's not so much safe, but anyway, so we can choose methane or methanol. And we have already know-how about handling this, so it's relatively easy for handling, easy, and also easy liquefaction. But however, so there's many programs such as selectivity of production. It's very difficult. We can both these three in one reaction in one device. So selectivity is one of the big program, and also carbon dioxide collection from the air. This is very thin, 0.03%. It's very difficult and can consume much energy. So CO2, carbon dioxide needs to be collected after usage and sent back to the location without renewable energy. So there's an extra cost and extra energy for sending back and of course collection. And another available element for the energy storage is nitrogen. Because there's plenty of nitrogen gas in the air, so 80% of the air is nitrogen. And if we react hydrogen with nitrogen, it can be ammonia. It's basically utilized for artificial fertilizer. This is not so much safe actually, but so much easier rather than the hydrogen gas. And we have know-how about the handling. So, and also only 10 atom is required to make ammonia as a liquid. So easy liquefaction. And as I said, so nitrogen can be obtained from the air and it can be emitted anywhere after usage. So there's no extra cost or energy like carbon. But the problem is ammonia synthesis requires severe reaction condition, 400 degrees and over 100 atoms. So it's not suitable for renewable energy because renewable energy can be very time variable, and also the concentration is not so much high. So this reaction condition is very difficult to be achieved by renewable energy. However, recently ammonia synthesis research is very developed. Recent research mitigates the reaction condition of ammonia synthesis like this. So 50 degrees and 1 atom. It's reported 2 years ago. So Hosono group in Tokyo University of Technology in Japan. Actually, I was a member of this group and it was actually very amazing. Please read some papers from the papers from that group. The characteristic of the catalyst is hydrogen storage and electron donation ability of the catalyst support. Usually, ruthenium is deposited on that support, and the support can donate the electron to the ruthenium. It can be very reactive, and the hydrogen storage capacity dissolves the hydrogen on the ruthenium. These two characteristics enhances the catalytic activity. And this reaction condition enables that renewable energy is utilized for ammonia synthesis. So there's a potential to be utilized for that. And I've introduced the scheme of the water, electricity, ammonia. So nexus production, I call it WA scheme. Here is one example of WA scheme. Please assume there's a pipeline which can convey the water. Actually, I assume the desert under the sea level, and so there's no energy to transport seawater. And in that case, seawater comes to the desert, and the seawater can be evaporated by the sunlight, and we can get the steam, and we can generate the electricity by solar thermal power generation. And we can get the water as a distilled, so using through the distilled water. And we can get the hydrogen by water electrolysis using distilled water and the electricity from solar thermal power generation. And also we can get nitrogen from the air. And if we react these two, we can get ammonia. If these three processes performed at once, we can reuse the waste heat. And also the process can be integrated. It means total number of processes decrease, so the cost for the making water or ammonia and electricity can be reduced. And also excess electricity and waste heat between each processes can be converted to ammonia as energy carrier, and energy, of course, energy efficiency can be increased. But actually, pipeline to convey the seawater is required from the sea to the city. So this is important. So current research objective, my research is shown here. So there's a trade-off reduction of CO2 emission based on the energy, but cost reduction by integrating the process. This can be possible, and CO2 emission and cost in pipeline construction transport energy. These are all trade-off relation. But in that case, the criteria to reduce CO2 emission and cost is not clear. So distance and elevation from the sea to a city, it's important function. So we evaluated the CO2 emission and cost as a function of these two, distance and elevation. So now we are investigating the many processes, and the important location, one of the important location is Jordan, actually. So because of the Red Sea Canal project. Background of Jordan is shown here. Population increased suddenly recently. So it becomes 6 million to 9 million within 5 years because of the refugees from surrounding countries and huge demand for water and food. And there's a project for the Red Sea project. Actually, now it's almost closed, actually, but another project is maybe also constructs a pipeline from the sea to the city. Anyway, so a lot of sunlight and seawater is in Jordan, and no energy requirement for the sea transportation if the pipeline is constructed, because the sea level of the Dead Sea is under sea level, so almost minus 400 meters. And I've also introduced about the desert under the sea level in the other area, such as Death Valley in USA and Salton Sea area also in USA, and also Shotmel area in Tunisia, and also Qatar Depression in Egypt and Lake Erie in Australia. And it's not under sea level, but the next shot in Mauritania, it's very close to the sea, and also the main population in here. So these are also the candidate for the WS scheme. This is also important area and produced to ammonia and water and electricity very efficiently. And actually, there's many patterns of WS scheme, such as using the reverse osmosis and using the photovoltaic power generation and kind of this. I also calculated these patterns using Aspen. This is a process simulation software, and we can know the cost for each processes using this equation. It's also published in the last year. Several patterns and several locations are possible for this WS scheme. So now I investigate the cost and amount of CO2 emissions. Some pattern is already finished. So now I already submit the papers for some journals. So it will be coming soon. And we are also examining the new catalyst for ammonia synthesis. This is also the experimental research. And if you are interested in our research, please contact us. And also let me introduce about the Kyoto University. If you come to my group, you'll be automatically become a student in this university. Here, the information about that. So the most number of Nobel Prize in Asia for this year, professor in this Kyoto University. So 90 medals. Actually, the second best is still in Asia. So in Asia, it's still the University of Tokyo, 16 medals. And it's Kyoto is surrounded by very beautiful and historical places like this. This is a write-up about the temples and shrines, in Kyoto. And also, it may be good for you. So Kyoto is a number 2 city that has the Michelin stars in the star, so 108 stars. This is a ranking. So almost 3 of 4 cities in the ranking for submission star is in Tokyo, Japan. Tokyo and Kyoto and Osaka. And Osaka and Kyoto is very close. So actually, this is a very leisure schools. It may be good for you and good fun. And please, if you please looking forward about that if you come to Japan. Thank you for listening. If you you're really interested in our scheme or some aspect of to be a student in Kyoto University, please contact me. The email is here, shown here. And actually, this is the homepage, URL for our group. So please visit this. Thank you for listening.
So thank you very much, Sensei, for the presentation. I'm sure that it was very informative, and now we can move to the Q&A session. So if everyone is having question or inquiry, please, you can ask to learn more about the topic. So I may start with a question from my side. So regarding the situation, Sensei, of like the water situation, wastewater, and the energy demand, what do you think about the potential of wastewater, for example?
It's the problem again. I couldn't hear so much.
Okay, can you hear me now?
Sorry.
Can you hear me now, Sensei?
Okay, now, okay, yeah, it's trouble again. Sorry. Yeah. Sorry. Can you ask me again?
Okay, so talking about the wastewater situation or water situation in our world nowadays and the energy demand.
Yeah.
What's your perspective on how can we resolve in parallel the wastewater situation and the energy demand from these aspects, Sensei?
From this aspect means, so my research area or research scheme, wastewater. Okay, wastewater. Actually, so now I only talk about the seawater, but the wastewater can be also utilized for the WS scheme. So yeah, it's possible if there's no, if people doesn't care about that. And also the water can be utilized for the agriculture. So the all of wastewater can be utilized, I think. And also, if we really use distilled water for that, yeah, so all of the heavy element, such as heavy metal, which is very harmful one, can be not disposed maybe, but so it's removed by just evaporation, very simply. So maybe better for the safe water. So yeah, so wastewater and other wastewater can be also utilized for that, and maybe very, very sure.
Thank you, Sensei. So by now, we can finish the meeting of the day, and bye-bye, everyone. Everyone, take care. Thank you, Sensei.
Thank you.
Bye.
Bye.